Okay, hello everyone. My name is Krivenkov, and I want to thank organizers for the great opportunity to present our experimental results on the topic of the semiconductor quantum emitters based on semiconductor quantum dots. It's a result of the about few years of the experimental work, and I want to present our team, which is based on the joint collaboration of the research group of Professor Yuri Rakovich and Professor Alexey Nikitin, Yuri Rakovich from Center de Physica Materialis, and Professor Alexey Nikitin from DIPC. And our group recently mostly interested in the producing of the materials for the quantum communication applications. So everyone knows what is qubit, and for the quantum communication we need to transfer these qubits, and we need the physical particles to encode qubits too. And one of the most useful way, let's say, encoding to the photon. However, for secure quantum communications, to produce these photons for this communication, we may not use the classical light sources like lasers, but which produce, for example, pulses of containing of the bunches of the photons. But we should use light sources which can produce pulses which contain only one photon per pulse. Also called quantum emitters. The examples of the quantum emitters, physical, can be fluorescent molecules, single molecules, it could be atoms, or could be semiconductor fluorescent quantum dots, quantum emitters. And now I will introduce a bit experimental parts because I will be talking about experimental results. So to measure the main parameter of the quantum emitter, single photon purity, we can use the simple experimental scheme containing the two photodetectors and the one beam splitter, so-called Hanbury-Brown-Twiss experimental scheme. And if we put the trace of the signal from our light source to this beam splitter, if we have only one photon per pulse, then this photon goes through this beam splitter either to one detector, either to other, not to both detectors. So if we measure the coincidence between these two detectors, we can calculate the most important parameter for us, or so-called second-order correlation function, G2 function. And for us, for single photon purity, for measuring single photon purity, is the most important, the central part of this G2 function related to the zero time delay between the two photodetectors. The lower level of the G2 function, as a zero time delay, the closer we are to the ideal single photon purity. So in the ideal case, it should be 0 here. In general, we don't achieve the ideal single photon purity. We still have some value. And we can consider the emitter or light source as a single photon emitter, as a quantum emitter, if the value of the G2 function is below 50% normally. For example, for the laser source, it will be 100%. So among other types of the quantum emitters possible, as I say, it could be molecules, it could be atoms, semiconductor quantum emitters, quantum dots, they have their advantages. I will be focusing today on the quantum dots, semiconductor quantum dots as a quantum emitters. They have very high photon absorption cross-section. That means that we can easily excite them. And at the same time, they have very high emission quantum efficiency, even at room temperature, reaching the 100%. Combination of this means that we can easily excite and produce a photon with almost deterministic probability. So we can, on demand, trigger the quantum dot and produce single photons from them, even at room temperature. Also, they have a short emission lifetime compared to many examples of other quantum emitters, and they have very high single photon purity at room temperature, even below 5%. Recently, our research group was mainly focused on the perovskite quantum dots, perovskite quantum emitters, and we recently developed the synthesis protocol, which allowed us easily synthesize very high quality perovskite nanocrystals with a cubic shape, almost cubic shape, and very high uniformity. And we can perform this synthesis at ambient conditions, at room temperature, so many research groups can reproduce it for their experiments. And not only their quality as a crystals we could achieve, but we could achieve the very interesting, very good optical properties of these nanocrystals on the level of single particles. By actually, what we implemented the doping of our nanocrystals with nickel. And it allowed us to achieve the high photoemissive quantum yield, more than 90%, for some samples almost 100%. Short emission lifetime, about 5 nanoseconds, and the most important, the very high single photon purity level, about 1%, and for some samples even lower, at room temperature. So all of these measurements were performed at ambient conditions, so in presence of air, in presence of the humidity, 55%, and room temperature. And for many people, the main problem of the, for many research group, main problem of the operating and working with perovskite nanocrystals, especially single perovskite nanocrystals at quantum emitters, is their stability, temporal stability of the under the photon excitation. To this moment, now for our samples, we could achieve the stability, spectral stability of our emission of single particle at ambient conditions, room temperature, humidity, air, more than 10 minutes for a single particle without any change of the spectrum, of their spectrum. And in total emission, like a lifetime, I would say these nanocrystals could be even longer than 20 minutes. To this moment is the highest stability level achieved at the ambient conditions among all perovskite nanocrystals. So these nanocrystals, these quantum dots, they could be used as sources of single photons at room temperature. However, there is another one, a very important parameter for the quantum applications, the indistinguishability of photons. So if what we can say about indistinguishability, if we produce a trace of single photons from our quantum emitter and we put two of them, consequent of them, to the beam splitter at the same time, if they are distinguishable, they don't interact, and they produce for different, like they can pass for different ways through a beam splitter. However, if they are indistinguishable, they can interact efficiently, produce full interference, and there will be only two ways of the interaction. But it's a result of that. But what the physics behind that, we also were talking today, people were talking a lot about T1, T2 parameters. So if we are talking about the quantum emitter, we are talking about emission lifetime, photoluminescent lifetime of the quantum emitter. It's a parameter T1. So if we Fourier transform this signal with a lifetime signal, then we will achieve the spectrum, energy spectrum, so-called Fourier transform limited spectrum. And in this case, we will produce indistinguishable single photons. However, on the practice, the spectral width of the quantum emitter is not Fourier transform limited, is much broader. Due to the different decoherence processes. So to achieve Fourier transform limited, we cannot use just quantum dots. Here you can see the Fourier transform limiting line for T2 and T1. And most examples of the quantum dots still not achieving this limit. So what can we do? To do that, we can try to compress the T1. We can try to compress the emission lifetime of our quantum emitters, our semiconductor quantum dots. To do that, we can couple them to the electromagnetic cavities, to their modes. And by implementing this light matter coupling with the electromagnetic cavity, we can implement the Purcell effect with coupling and compression of the emission lifetime. There are different types of the cavities which can be used for this light matter coupling. Could be microcavities, could be photonic crystals, or it could be plasmonic nanocavities. And if we estimate the limitations of each type of the cavities, we can see that the highest values of the Purcell factor which we can achieve principle are from the plasmonic particles. That's why our group were focusing mostly on the coupling of the single quantum dots with plasmonic cavities to achieve this lifetime compression. So we performed the coupling of quantum dots with different types of plasmonic cavities. So we could achieve the Purcell effect, which means the compression of the emission lifetime, shortening of the T1 for quantum dots. We also could achieve the increase of the emission intensity by the coupling of the excitation field with plasmonic cavities, and leading to the increase of the intensity or the photon flow from our quantum emitters. And we also could combine these effects to achieve both compression of the lifetime and the increase of the photon flow. In our case, it was up to 13 times, more than 13 times. But we also faced the other one, important feature in quantum dots we were coupling, which is related to the possibility of producing of the photon pairs from the single quantum dot. Indeed, if with the same time, if we realize a two-photon absorption by the quantum dot, then we produce a quasi-particle, so-called B-exciton, consisting of 2 electrons and 2 holes in the same one nanocrystal. And this nanoparticle can recombine with emission of 2 photons throughout the intermediate exciton level. So from the big exciton state to the exciton state to the ground state, producing 2 photons, photon pair. And if these 2 photons are coming from the same quantum states, they can be quantum entangled. However, there is like one problem with, in general, with semiconductor quantum emitters, is the presence of crystal field leading to the fine structure splitting, which is ruining the entanglement of the photons produced from this cascade recombination, because different polarizations will have different levels, intermediate exciton level energy, which is ruining this situation of the entanglement. And if we will look for the quantum dots, how it will be related to the parameters, the entanglement fidelity, we will see that it's also very important the lifetime of the intermediate exciton state. So shorter this lifetime, the less effect of the fine fraction splitting affecting the system. So it's still quite far away, to be honest, from the achieving any entanglement fidelity from the colloidal quantum dots. So to this moment, the lowest level fine structure splitting is 200 microelectron volts, and the shortest lifetime achieved with the cavity 13 picosecond. So we still need 10 times more to achieve some levels of the entanglement fidelity, but it's still work which we are performing, we are doing. So we were, what can I say about the coupling of these big exciton transitions to the plasmonic particles? First interesting thing is that plasmonic particles have broad spectra, so you can see the broad spectra. Broad band, so we can couple both big exciton and exciton transition to the same cavity mode, which allow us to increase the efficiency of the both emitted photons. So we can produce very efficiently photon pair, still not entangled, but with a quantum yield of the big exciton transition very high. So it's about, we achieved like almost 50%. 2 minutes. Okay, so what can I say? But at the same time, we change the statistics of the photon emission. We change from the single photon emission to the multi-photon emission, for emission photon pairs. So we're wondering if we could control it on demand or deterministically. And yes, we can do that. So we can look at the same quantum dot before the interaction. We can look at the during interaction, plasmonic particles after interaction. And yes, we can switch. We can switch the emission transition from the single photon emission statistics to the emission of photon pairs and back to the single photon emission with the changing of the emission lifetime. Also, we could achieve the situation where we had the conserving the single photon purity of the quantum dot coupled to the plasmonic particles, and at the same time with compressing of the lifetime. For that, we needed to shift the emission spectrum of the quantum dot out of the maximum with maximum of the plasmonic band. But this situation we experimentally achieved. So yes, so this is this is most of the results which we achieved in the last years. I hope that I convinced you that semiconductor quantum dots can have potential, can be room temperature, single photon emitters, also have potential for future application. The sources for distinguishable photons and entangled photon pairs. Thank you again for your attention, and thanks organizers for this great opportunity to present our results.
Yes, thanks for the talk. I was wondering how this works so well in room temperature. Doesn't like coupling to phonons or the material or so affect the indistinguishability of your photons? Or isn't there a decoherence mechanism that you actually see due to being in room temperature?
So as I said, to achieve indistinguishability at room temperature, I don't know, it's quite far away task. The indistinguishability can be achieved at cryogenic temperature, but with the same effect of the coupling with the cavity. But single photon purity itself, as I will show here, single photon purity itself at room temperature, yes, it's achievable because in
purity is when that you are sure that there is one photon, right? That's
yes,
purity?
exactly.
Okay.
Yes, then we are sure that we don't have second photon because actually in semiconductor quantum dots, there's not ideal single photon purity is actually related to the big exciton emission, as I showed you later. When we increase the big exciton emission, yeah, here, we ruining the single photon purity. But if we eliminate the big exciton state at all, then as we performed in our perovskite nanocrystals, where the efficiency of the big exciton transition is almost zero, then we don't have the second photon coming from the quantum dot, and we also always have only one photon. So it's interplay what we want to achieve.
Oh, thanks.
Thanks. I have a question related to these bi-exciton emissions. So you see two photons. Could you use this also as a heralded single photon source? And how do the quality of the single photons that you get from that?
So if you use them as single photons, unfortunately, they're not indistinguishable because they have different energy. Because this transition and these transitions they have.
But you could use the first one of one frequency as a herald for the second one, and I was wondering if this...
Then they're still not coherent. So again, so for that.
No. I'm just asking the second this. So you detect a photon, and then you say, because you know you're in the two photon emission rate, another one has to come quickly after that. So I would expect this then to be a good single photon, but it might be different from the single photon you get from single photon excitation. I was wondering if you can compare these two ways of creating a single photon.
It's a good question. Because they have the same polarization, I don't know how to separate them specifically to put single exciton like this transition to one direction, the other photon to the other direction. I cannot answer how you to implement it experimentally, but probably it's possible, yes. It's a task.
Okay, if there are no more questions, let's thank the speaker again.